Continuing on with a definition, a matrix A is called symmetric if the matrix is the same as its transpose. So on the one we just did a little while ago, it was 4, 2, 2, 1, and notice what happens if you transpose this. It's still 4, 2, 2, 1. And so that means this is a symmetric matrix. So again, symmetric is something you may have seen in another class. Maybe you did, maybe you didn't. But it's a relatively basic concept here. I mean, there's not really much to it. It's just you take the transpose, you get back to itself. But it turns out that there are some really important properties for a symmetric matrix. I'll give you one quick one here first. So theorem, the eigenvalues of symmetric matrices are always real numbers. So you may or may not have had any examples in your other classes where you tried to find eigenvalues and eigenvectors, and the eigenvalues ended up turning to be imaginary numbers, and it was probably a real pain to try to find the eigenvectors. So that can happen in general. There are matrices like that. But it turns out if you have a symmetric matrix, that's not going to happen. They're always going to be real numbers. So that's one use of it, right? If I ever give you a symmetric matrix, you're guaranteed to have real numbers here. But there's another property of symmetric matrices, and this is the one that's really going to be useful here, is that if you ever have two different eigenvalues of specifically a symmetric matrix, and you have corresponding eigenvectors x1 and x2, then x1 and x2 will be orthogonal, perpendicular. So it is not true that every matrix you have, you're always going to have eigenvectors that are perpendicular to each other. But it is true that for symmetric matrices, your eigenvectors are going to be perpendicular to each other. And so this then kind of ties into the following here, which is the big theorem for this section. It's called the fundamental theorem of symmetric matrices. And it says the following here. A is orthogonally diagonalizable with real eigenvalues if and only if A is symmetric. So what that means is the only matrices that you can do the whole orthogonal diagonalization that we saw earlier are symmetric matrices. That's it. So that means on your exam, when I give you a matrix and say, find the orthogonal diagonalization of this, well, guess what? It's going to be a symmetric matrix. Otherwise, it wouldn't work. So this is, a fundamental theorem. So some fundamental theorems are really useful to calculate things. For example, the fundamental theorem of calculus is incredibly useful for doing calculations. On the other hand, some are more just giving an important fact without being useful for calculations. And this is one of those here, because this isn't really going to help you calculate the orthogonal diagonalization, but it does tell you the only situation in which you can find an orthogonal diagonalization. So regardless, this is not necessarily going to be something that you need specifically for what we're doing in this class. It's more like this is why we give you these problems. But you can absolutely expect a problem on the exam that says, here's a matrix, find the orthogonal diagonalization. It's also possible that I will give you another problem that says, here's a matrix, is there an orthogonal diagonalization? And in that case, you could try to find it and do a bunch of work. Or you could use this theorem and say, hey, wait a second, that matrix is not symmetric, therefore it is not orthogonally diagonalizable without doing any work at all. So regardless, you don't have to memorize this theorem, but it could save you work if you're trying to figure out which one can be done and which one's impossible.